Okay, I'm going to collect these in 1 minute. So anybody who wants to turn in their problem, turn it in. We are nearing the witching hour. And again, I'm going to be kind of hard-nosed about the timing issue this semester, just because the class is so large. It's going to be very disruptive if people turn things in the middle of class. So we've got 25 seconds. Okay. Fair enough. Okay, let's think. First of all, are there any questions, logistical or technical or anything like that, about the from the first lecture? Any questions about the homeworks or the procedures or anything like that? Okay. I got a couple people talking to me about I got a couple people talking to me. Uh-oh, trouble. Wait. No. That's bad. Okay. I managed to turn off the projector, which seems like a bad thing. Okay, we'll try to get that on. So I had a couple of people asking me about the homework, the extra credit things from the programming contests. Again, I put on the webpage a description of a small number of programming contest problems, which have some algorithmic content, which people who are interested in can do for fun. Okay, if you go to the webpage, you should see it. There will be a very small amount of extra credit for it, not enough for anybody to do this for greedy. So if, let's say, you're having problems in this class, should you be doing extra credit or should you be working on the regular stuff? You should be working on the regular stuff. Is that clear? The extra credit is for the people who don't need it. Okay, that's an important point about this. Any questions about that? Any other questions about the organization or technical things or anything like that? I'd like to get started. Okay, projector on. Okay, you put whatever you want there. Okay, okay. So let's get started on the problem of the day, which hopefully will start to come back here now. The problem of the day has to do with finding counterexamples. So in last class, what I think was, maybe one of the more important things I said last class was about finding counterexamples. The importance that when we think about algorithms, we have to think about them critically enough to realize that they are probably wrong. Okay? There's a large number of algorithms out there. One of them is right. Yours is probably not it, at least not the first time you try to think about it. And so it's important to learn how to think critically and know how to look for weaknesses in your algorithm. And, there are a couple of strategies. I had a slide on there from last time. I'm not going to go over this slide, but I want us just to think about it. What kind of ideas should you use when looking for counterexamples? One is to look at a lot of small cases. Usually, if an algorithm breaks, it will break on a surprisingly small case, okay? And so one thing that sometimes people will do is try to come up with horribly complicated things and say, look, it's wrong, okay? But if they make a very complicated example, they can't prove to themselves what that algorithm is going to do on it. And they usually get lost in how they're thinking about it. So the best counterexamples are usually simple, clear, crisp, and when everybody sees them, they agree that it's wrong. Okay? Any questions? Another thing that is often good is to try to force ties. Again, we'll go through this and we'll take a look at it. Where there are two alternate things to look for that are equally good. Okay? And if the algorithm has two choices of these things and you haven't really specified how to break ties, that is often enough to confuse it because quite possibly it will pick the wrong one. Okay, that's a good general strategy. And, it's something you just got to learn to think about and look critically. Any questions about the basic idea of counterexamples? A couple students came up to me last class afterwards and said, what do you mean we're not supposed to prove our algorithms correct? All we're supposed to do is prove them wrong. And that's not what I meant to say. What I mean to say is when we talk about algorithms, correctness proofs are important. But to understand whether your algorithm is right or not, you need to have some kind of an idea, an intuition, some confidence in it. Okay? And just mechanically writing a proof for something is often very misleading because it's very, very easy to fall into a bad way of thinking about it. And so that's why I want to talk about counterexamples a little bit. Any questions? This needs to be part of your general toolbox. So, okay, so let's talk about counterexamples. The problem of the day today is on something called the knapsack problem. And it's a famous algorithm problem where the basic property is that you have a thief, okay, who has a knapsack, okay? They break into a store. There's a certain number of objects, okay, certain objects that they'd like to steal. They'd like to steal as much as possible by putting it in their knapsack. The trouble is the knapsack has a finite capacity, okay, and an object isn't worth anything if you break it. Does everybody agree with that? You know, if you have an iPhone is worth, $500. Half an iPhone is worth nothing, right? Okay, so we have our problem where there is a knapsack capacity T, and there are a set of objects here, okay, which are specified by their weight or size. And the question is, find a subset of these items. Let's say there's n items here. In this case, example, it looks like they were 1, 2, 5, 9, and 10. Find the subset that adds up to the target. The claim here is that if the target is 22, then you can find something that adds up to it. Which numbers add up to 22 from looking at that example? Does anybody have yes? 1 and 2 and 9 and 10 is 22. The claim is that there's nothing here that adds up to 23. There's no way to make those numbers, a subset of those numbers, add up to 23. Okay? Any questions about that? Okay? Can anybody give me a correct algorithm, absolutely correct algorithm, for given a set of n numbers, okay, finding out if there is a subset of them that adds up exactly to the target? Okay, yes. Well, okay, let's think about that. I think that's one of my problems here a little bit later. How can anyone give me something that they absolutely are sure is correct? Okay, yes. Brute force. What is brute force here? Try all subsets. Well, okay, it means all possible subsets of those numbers, right? So that would mean that if we have 3 numbers, A, B, and C, it means the possibilities are the empty set, number A, number B, number C, A plus B, A plus C, B plus C, A plus B plus C. If we have n numbers, how many possibilities are there, okay, for all possible subsets? 2 to the n subsets. How many people know what that means? If you don't feel too bad. How many people don't know what that means? Okay, how many people didn't answer? Okay, when I ask these things, I need answers, so I need to get a sense of the crowd. Okay? Okay, so let's think. Any questions about what the knapsack problem is and why it comes in handy? Okay? Any questions about it? This is a practical problem that again, robbing things from a store is not a practical problem. But the idea of finding a bunch of things that add up to a limited packing capacity is this is the problem that comes up in any kind of a packing problem, okay? And so it's basically that kind of a problem. Okay, but I ask you now to give me a counterexample to the following algorithm, okay? Meaning that I want you to come up with a set of numbers and a target such that for the given algorithm, using your algorithm on those numbers with that target does not leave the knapsack full even though there exists a solution. So let's take a look at this. And I think I want to start with, you in the back said you think the following algorithm seemingly is right if I am correct. Okay? I think if I understood what you said that one way to, given a target and given the subset of numbers, might be to fill them up from largest to smallest. Okay, so wait, let's try your procedure, let's see if we can find a counterexample to it. So what is your procedure again? Specify it clearly. Yes. Start from the smallest one. Biggest one. From the beginning. What? So in other words, let's just think about what you're saying. Is it that you're going to start from the beginning, you keep stuffing, that you have them from biggest to smallest. You stuff the knapsack with each number if it fits. Then, if you can't fit one, you throw it out and you keep going. Oh, okay. You're saying, no, go back to the beginning and do something more exhaustive, something like that. Okay, maybe. Let's go and take a look at these heuristics then. Now that's getting a little complicated and I don't know. But let's look at these algorithms and see if we can come up with a counterexample. Problem number 1 says, I want to know, put the elements in left to right order, okay, if they fit. Can someone give me a set of numbers and a target that will do it? Okay, what's your proposal? 1, 2, 3, 4, 5. Okay, so he's saying for this one, 1, 2, 3, 4, 5. And the target is 11. Oops, we in trouble now? Probably are. 11. Okay? First of all, is there a solution that adds up to 11? And I think I see it, right? What is this algorithm going to do if it's left or right? It's going to say 1 is good, because now I have a room to 10 left. 3 is good, 2 is good. Now I have 3 in my knapsack, meaning that I have 8 left. Here, I put this in. I've now got 6 in, meaning I have 5 left. I put this one in. Now I've got 1 left, right? Does everybody see it? But now I can't put this in anymore, right? Number 5 doesn't fit because I only have room for 1 more, right? So here's an example where putting them in from left to right order, okay, does not yield the right answer, even though there is a right answer, okay? And I think, there are a couple of different ones. What's an example of a right answer? I guess 1, 2, 3, and 5, okay, would be a right answer. Any questions? Do people see why this example is a counterexample for that algorithm? Can anyone come up with a simpler example? I find this is complicated. Too many numbers in it. Yes? 1 and 2. Okay, now this to me looks even better, right? 1 and 2, and my target is 2. Okay? You put in 1 and you lose. Does everybody see it? So this heuristic is bad enough it fails on only 2 numbers. Does everybody see that? Okay? And when you look for these things, simple counterexamples are easier to find and analyze than harder ones. Any questions about that? Okay? What about the next algorithms? We put them in from smallest to biggest. Can anybody come up with a counterexample for this? Okay? Yes. Both of them on the board already. Which one is better? Well, to my mind, the second one is better, right? You start from smallest to biggest, okay? And this particular one, is the answer, right? So this doesn't work. This doesn't work. Now, could someone give me a counterexample where we fill the knapsack from largest to smallest? Yes. Okay, so you want to say 1, 2, and the target is 1, and that I don't believe, actually. So you want to say 1, 2, and the target is 1. What is going to happen? You're going to try to put 2 in the knapsack, and you're going to fail. And then you're going to go move on to the next item and put 1 in, and you're going to succeed. Does everybody see that? You're going to move from left to right, keep putting them in if they fit, okay, and make a sweep through the items, okay? If that's the algorithm, if we agree that if you put something in and it failed, you gave up immediately, then that would be a counterexample. But suppose, let's say we're going to go them left to right, one by one, see if they fit. If so, put them in. Okay? What's yours? 4, 3, 2. You're saying 4, 3, 2. Let's try that one. 4, 3, and 2, and the target is 5. You're saying that if I put this thing in, I'm going to get 4, Now I have room for one more. 3 won't work, 2 won't work. So the most I have a 4 in here, when if I had been a more omniscient, I would have seen I could get 5. Does everybody see that? Any questions? Okay, does anybody have a simpler example? Probably not. Okay, 3 I think is probably about the minimum here. Okay? Yes? What about 3 and 2 and target 4? Well, okay, so for 3 and 2 and target 4, 3 and 2 and a target of 4, here, if I go from left to right, from biggest to smallest, I will put 3 things in the knapsack, right? The trouble is I can't come away with 4, right? So there's a difference between an example not having a solution, okay? If I give you a problem on the homework and it has no solution, is it fair for me to take off points? Well, you might say no, okay? I don't make any promises, okay? But that's a different question, right? Here's a world where there is a solution and you can't find it by your procedure. That's really what we're looking for, okay? Any questions about any of these things? Yes? Are the first algorithms equivalent on sorted data? I guess the answer is yes, okay? So there are different, there are different heuristics that you can think about. Smallest to largest is good. So these are things that are heuristics that often work pretty well at getting something in your knapsack, okay? So if, in fact, you break into the jewelry store and, the alarm's going off and you have to quickly fill your knapsack, I recommend one of these 2, okay? But on the other hand, you're not likely to get the optimal solution, okay? And in fact, this is another one of those hard problems where there really is no better way to do it than searching through all possibilities, okay? So in fact, if you tell me you've got a very fast algorithm here, I'm going to tell you you're wrong, okay? But we'll discuss that at the end of the semester. Any questions about that? Any more questions about the daily problem? Okay, good. Okay, so let's see if I can move on now. Clear, bunk, and bunk. Okay, so what I'd like to talk about here today is the sort of the fundamental, let's say, model of how we are going to analyze algorithms. Okay, so we need a way to keep score. And there are 2, let's say, big ideas today. Okay, and it's important that you understand each of these big ideas are separate things because people sometimes get confused. Okay, we're going to talk about what is a model of how computers behave and how we can measure how much time an algorithm takes on a computer. And the other is a notation for talking about functions. Okay, and that's the big O notation. These are 2 separate kinds of things, okay? How many people here have already had some discussion of the big O notation? Okay, a lot of people. How many liked it? Okay, a few. Okay, very few. Okay? But what we're going to look at is the big O notation. Again, we're going to use the RAM model of computation to describe a basic idea of how computers work so we can reason about them. The big O notation is going to be about how can we talk about complicated functions in a simple way so it's easy to think about. Okay, and these are 2 separate ideas. Any questions about that? Okay, so the first thing we're going to talk about here is the RAM model of computation. And if you think about it, if historically the development of algorithms was built around the special computer architecture that was in use at the time, okay, the history of algorithms would be an ugly thing, okay, because computers change all the time, right? I mean, in my day, I remember when I had a Z80 processor in my early computer with 64 kilobytes of memory and stuff like that. And computers today are wildly different and more powerful, it seems, okay? But there is something, if we abstract computers today enough, we can come up with a simple model of what computers do that applied then and will continue to apply for the interesting part of what computers do in the future. And this is what we call the RAM model of computation. RAM stands for Random Access Machine. Okay? And what do we care? So what does a computer, again, it's going to let us analyze algorithms in a computer-independent way and a language-independent way. So what are we going to assume about our languages, about our computers? First, a program in our language is going to be made up of lines of code. Okay? And each line of code is going to be made up of individual operations. Adding two numbers, subtracting two numbers, comparing two numbers, multiplying two numbers, okay? Testing if this number is bigger than this number. Each elementary thing that gets done in a computer program is going to take one step, okay? That's what we're going to say, okay? One cycle, one computron. If you think of a computron as the elementary unit of computation flowing through your computer. One computron gets eaten every time you do an elementary step. Okay? Things in programs that involve loops, recognize, are not things that get done in one computron, right? If I have a loop that goes 4i goes from 1 to 1,000,000, that loop is going around 1,000,000 times. And so it is really doing 1,000,000 things and not one thing. Does everybody get that? Okay? So we're going to basically say that every individual step that corresponds to an instruction on a machine as it gets executed is one step. Okay? Any questions about that? Okay? When we call a subroutine, if we say call a subroutine sort, recognize that there might be a lot of steps hidden in the subroutine, right? And so when we count these things, saying sort this, that's not a one-step operation. That's however many steps the subroutine takes. Okay? So we're fairly going to count how many instructions get executed by the machine. Each one gets charged 1. Okay? Any questions? The other thing we're going to do is say that whenever we access memory to read or write, okay, it takes one step, 1 unit of time, 1 computron. Okay? Any questions about that? That's what it means by random access machine, right? If we lived on a magnetic tape, Alan Turing, you've probably heard of Alan Turing and Turing machines. He thought computers, worked on tapes. And if so, to get access to this memory, you would have to slide the tape head over there to read it. That's not for us. We can go to any point in memory and pluck out what's in there in one step. Okay? Any questions about what the basic machine is? Okay, what we mean by a RAM machine. Now, this is a model of computers. How accurate a model of computers is it? Let's sit down and talk about it. From what you know, does every memory access in your computer, many of you are sitting here using Facebook or something during lecture, okay? Your computer's doing something, right? Is every memory access on your computer taking one step? Okay, in what way is it not doing it? What's the story of your computer's memory? Yeah? A hard drive is slower, right? A hard drive is 1,000 times slower than regular memory, right? And it even gets worse. You've got all this cache memory and registers and forget it. Okay, so this is not true in a real computer. But the fact that it's not true is not going to be important to us. We're going to ignore that detail, and we're going to be usually extremely happy ignoring it. Okay? Basically, each memory step takes one regardless. We're not going to worry about registers or cache or disks or anything like that. Is it true that every operation on a computer, a basic instruction, takes the same as every other instruction on a computer? Okay? Can anybody think of 2 arithmetic operations that take different amounts of time? Yeah? Usually, when you implement things, multiplication is a harder thing to do on a machine level. So it might take, 1 nanosecond to do an addition, where it might take 5 nanoseconds, something like that, for a multiplication. So that's also not true, really, okay? But we're going to ignore it, okay? Why are we going to feel good about ignoring these things? Because it's going to make for a simple model of analyzing algorithms We're worrying about the details of caches and disks, and the instruction set of your computer requires knowing about a lot of things that ultimately don't matter to us. Okay? I don't know any of this stuff. Okay? And it's very, and it's something that we are safe ignoring. Our RAM is designed to be a simple model, okay, of how computers work, and simple models work well. Any questions about that? Okay, yeah. Okay, so you're saying that if we want to use a more advanced model of computation, then if you use a different model, you might get a different measure of the performance of the algorithm. What I would say, this model has worked very, very well for 50 years, okay, and basically mirrored what computers do and enabled you to come up with a nice way of thinking and analyzing algorithms. So this is a robust enough model to have been useful for, the most kinds of things, okay? And so it's a model I feel very, very good about, okay? Any questions? Again, simple models are usually better than more complicated models. For example, like I said, the model of the Earth being flat. Who here believes the Earth is flat? No one, okay? Who here checked when they went to the shoe store to make sure that the bottom of their shoe was beveled so that they could accurately hug the curved Earth underneath them? Okay? The answer is no. You wanted to make sure the bottom of your shoes was flat, right? Because on the scale that you are reasoning about the Earth, it is usually flat, right? And likewise, on the scale that we're going to be reasoning about algorithms, all this stuff about cache and stuff like that is a secondary concern. Yes? Okay, so now he says quantum computers. That's an interesting thing. So in general, the computers that we're talking about today are modeled by these RAM models of computation, and they work very well. Now, what he's noticed is that there is a theoretical idea of a new type of computer called a quantum computer, okay, which doesn't physically exist yet, but people seem to think they can build one, okay, and they seem to think that if it works according to the laws of quantum physics, you can compute certain things in a wildly different way than the way we're going to talk about in here. So I will agree with you that a quantum computer will work wildly differently than everything we talk about in here. Okay? And I promise that when we start getting quantum computers, I will teach a course in quantum computer programming. Okay? But at the moment, we don't have these things. Okay? And so we're not going to talk about quantum. They actually are theoretically quite interesting. Okay? And it's not ridiculous to believe that something's going to happen with them. Okay? But for our experiences, it doesn't inform anything. Any questions? Yes? Okay, so he recommends a book. There's a lot of books out there. There's a lot of things out there. We're not going to deal with quantum computing in here. Okay? Any questions? Okay, good. We are going to deal with the RAM computation. Okay, so now we know how computers work. Okay, which means that if I take any programming language on any computer, I can break down, if I give that algorithm, that program, an input, okay, I can count how many steps it will do on that input. Does everybody agree that if you take a program and you take an input and you run that program on the input, it's going to execute a certain number of steps on that input, right? You can count that. That's a discrete thing to count, right? And so what's interesting is every program in the universe sort of defines a chart like this, okay, where the x-axis here is going to be the size of the input. Let's say it's a program for sorting. The size of an input an input to a sorting problem is how many items are you going to sort, right? You might sort one thing, you might sort two things, three things, four things, ... n things. On every possible sorting input, your program is going to take a certain number of steps. We can make a graph where the x-axis is the problem size The y-axis is the number of steps. And there is a dot for every input, okay, which is going to say for every input there is a size, and given your particular program, there's a number of steps it takes to sort it. Okay, how many people are with me at this point? Okay, some, but not everybody. Okay, what are the possible inputs to a sorting program that are three items? Okay, if my items are A, B, and C, what are my possible inputs? Uh-oh, trouble. I have A followed by B followed by C, A followed by C followed by B, B followed by A followed by C, B, C, A, C, A, B, C, B, A. Does everybody agree that if I'm going to have three inputs to a sorting program, there really are only 6 possible input files? Does everybody agree with that? And if I'm sorting 3-element files, there's 6 elements here. If I give you a sorting program, each one of these is going to correspond, this one is going to use 47 steps. Oops. Which hopefully, let's try this. Oops, let's try this here. 47 steps. This one over here uses 96 steps. This one here uses 23 steps. Does everybody see what these points represent? Each dot is a particular input file, okay? And we have it filed under its size, and when we run it on a particular sorting program, there is a given number of steps, okay? Any questions about this, what I mean by these dots? Okay? It should be clear that as a thing to reason about, any program, okay, generates a picture of these dots, okay, on where the x-axis is size and the y-axis is time. Any questions? If so, we can start to think of certain interesting lines going through these dots, okay? This thing at the bottom is the best case, okay? What does that mean? This is the input which used of all inputs of size 4, this is the one that used the smallest number of steps. Does everybody see that? So if you want to give a demo to the teacher, which input should you be feeding your program? The best case, right? Zips through it, okay? Likewise, there is also a line that goes through a curve that goes through the inputs that took the most amount of time. That represents the worst case running time of the algorithm, okay? And you might define other kinds of lines, like maybe the average of all these things, okay? And that would be a line that somehow sits between them, okay? And it's these lines that are going to be the running time complexity of the algorithm. That is what we seek to learn by analyzing it. Okay? Any questions so far? Okay? So recognize that we could, in principle, take our program, make sure we feed it all possible examples, construct this graph. But that involves running things, it involves constructing all things, it's complicated. What we would like to do is to be able to analyze algorithms, look at them on paper, okay, and see if we can predict what the shape of this curve is, typically. Okay, the worst case running time of the algorithm. Any questions about that? Okay. Oops, let's see if we can do this. Bunk. Clear. Bunk. Okay? So the important thing is, when we talk about any algorithm, there are functions that are a function of n, the size of the input, okay, which measures the best case, the worst case, and average case complexity as a function of time. Any questions? Which of these do we think is the most meaningful one? Okay? There is a best case time, there is a worst case time, there is an average case time. If you want to know how good an algorithm is, which of these, who would like to speak for one of them? Yes. You think the worst case is most important. Why is the worst case most important? Should always expect the worst, right? Right. You know, if the credit card company tells you we're going to charge you 20% interest or 1% interest, okay, what are they going to charge you? Okay, you know, okay? Worst case, okay? So the worst case time, in some sense, is the pessimistic view of it, okay? And what turns out to be good about it is, first of all, you're not surprised. And second, it turns out to be something that usually you can figure out an analysis of the worst case time pretty easily, okay? So that's why, in general, we're going to talk about worst case, okay? It is useful as a pessimistic view, and it also turns out to be relatively easy to obtain by analysis. Any of these other things that people like? Yes? Okay, so you're saying you like average case because you think average case is real. And on one level, that might be true. On the other level, the question is average over what? Okay? So let's take a look at this. What is the average weight, okay, of people, the average weight of people? Is it the average of the people in this class? Is it the average of the people in the United States? Is it the average of the people in the world? You will come up with wildly different answers there, right? So when you talk about, you know, real world, well, the difference there, it depends upon which real world you're living in. Are you living in the class world, the United States world, or the world world, right? Okay? So it turns out that it's a little bit tricky, although it's appealing to think about the average case, okay? Usually you don't really know what you mean by average in terms of what you will encounter, okay? You don't know what situations you will encounter. It's also the case that when people do a convincing average case analysis, and we will do a couple in here, okay? The math there is usually a lot more complicated than the worst case. So for many algorithms, I'm scared to do an average case analysis, whereas a worst case analysis is usually straightforward. Okay? Any questions? Yes?
How do you reason about
the best worst case of a problem? I don't know what you mean by the best worst case of a problem.
Best algorithm whose worst case is the best of all algorithms for a problem.
Okay, so what we're going to do, okay, let's not go there yet. Okay, we'll talk about this a little bit later, and then maybe we'll talk about that later. Okay, because I want to develop things a little bit. Any questions? Okay. So what is important to us? If we think about a curve like this, let's say we now agree we are interested in the worst case analysis, the worst case complexity of an algorithm. That is defined by the single highest point, okay, as we go through it, as n gets larger. What I can tell you is if you look at a real program and you do a real experiment like that, the worst case complexity as a function of n is going to go through all kinds of strange little gyrations. It's not always the case that the worst case for 8 examples is going to take more time than the worst case for 7 examples. Okay? There are sort of weird properties there. And so if you really want to get the exact worst case time of your algorithm, you are talking about a very, very messy problem. Okay? A very, very messy, idea. Okay? And certainly it's not going to be the kind of a function that is described by algebraic things like you're used to, and squared and cubed, things like this. Okay? So what we're going to do in here, the best way to talk about messy functions is to sort of approximate them by smooth and simple functions. Okay? And in particular, we're going to talk about our functions in terms of upper and lower bounds. Okay? So here, squiggly line, is the function that in principle we care about. It's too complicated to talk about. But if we can say it's always less than this simple function, and always greater than this simple function, then we have an idea of where this function wiggles between. Okay? And that is what's going to lead us to talking about the big O notation, which we've already established many of you have heard of and very few of you like. Okay? Any questions about that? Okay? Let me say why we want to do this. Again, there's going to be mechanics we have to learn about working with these things. But it's important to understand why these things exist in the first place. Any questions? Okay. So what are the names and meaning of these different sort of bounding functions? Okay? When we say the big O notation, what we mean here, let's try this, ka-chunk, okay? When we say that a function g of n is big O of f of n, what we mean is that there is essentially that f of n is an upper bound of g of n. Namely, there is something you can multiply this by, c by, okay? You multiply f of n by, so that this is bigger than that. That's really what it means, right? If f of n is an upper bound of g of n, that really means that f of n is bigger than g of n, right? There is also the omega function. The omega function is a lower bound. This is upper bound, lower bound. Lower bound means that our function we care about, g of n, is always bigger than f of n. That's what it means when it's a lower bound. It's something below it. Okay? Meaning that there is some constant times this, okay, such that this, okay, is less than this. Okay? Any questions about that? We'll look at examples in a minute. We're going to go through a couple of examples for the rest of the day. Okay? But understand the idea that when we have an upper bound and a lower bound, we also have something called a theta, which means a tight bound. Okay, tight. Okay? If we say g of n is theta of f of n, that means that f of n is both an upper bound and a lower bound, meaning that the behavior of this thing is essentially the same as the behavior of that thing. Okay? Any questions about that? Upper bound, lower bound, tight bound. Okay? Any questions? Okay, let's move on. And what I'm going to tell you is, in working with this notation, at the beginning, it's going to be complicated. You're going to get confused. What I will say is, the moment you are confused, your job is to go back to the definition. Okay? These are definitions of notation. Okay? And whenever you're confused about something, just go back to the definition and see what it says. And then you can reason about it well. Any questions? So let's think on a graph sense what this means. Okay? If I have the big O notation, what does this mean when I say that f of n is less? If you look at this thing, what is happening here? My function f of n is less than some constant g of n times g of n. Right? If you read what this says, this is c times g of n. That means that this function here is an upper bound of that. So what is this graph a way of saying? It's a way of saying that f of n is big O of g of n. Okay? Does everybody see that? F of n is upper bounded by g of n. Any questions about that? What does this figure say? This figure over here says that here we've got f of n, and it's always bigger than some constant times g of n. So what can we say about the relationship between f of n and g of n? G of n is a lower bound of it, right? So what does that mean? That means this graph is a way of saying that f of n is omega of g of n. Any questions about that? Here, in the third picture, we've got that f of n is sitting straddled between something that is C1 times g of n and something times C2 of g of n. Does everybody see that? What do we know about the constants C1 and C2 based on this picture? Is there any relationship between the numbers C? This is C1 times Gn, C2 times Gn. If you look at this picture, do you know anything about what C1 is and what C2 is and what their relationship is? Someone with a hand. Yeah? What? C1 has to be greater than that, right? If C1 is equal to, let's say, 10, and C2 is equal to 2, then is it true that 10 times Gn is going to be bigger than 2 times Gn? The answer is yes. Does everybody see that? And if f of n is, let's say, equal to 3 times Gn, or 4 times Gn, or 4.5 times Gn, that function is going to sit between C times Gn, C1 times Gn, and C2 times Gn. Okay? Yes? Shouldn't C1 and C... Okay, so you're saying that if, in fact... so what you're saying, really, is you don't like the shape of the curve here. Okay? You are saying that if, in fact, this is, let's say, if this was Gn, then any constant times Gn, if it was a constant bigger than 1, it would be a straight line also. And if it was a constant less than 1, it would be a straight line also, but lower it. You're 100% right. Okay? So consider it, so this function is not, don't consider this to be a cartoon rather than an actual plot. Okay? Does everybody agree that if you take a constant and you take a function, you multiply it by a constant, it translates up or down? Okay? Any questions about that? Okay? But do people see, this is sometimes a mystery, and I want to make sure it's not a mystery now. Doesn't it look kind of funny that f of n here is upper bounded by Gn and also lower bounded by Gn? How would that be possible? The reason is because we're multiplying it by a constant. Okay? If I take my salary, if I multiply it by 1 billion, it's going to be higher than anybody in this class, right? And if I take my salary and I multiply it by 0.000000001, it will be less than anybody in that class, right? So it's, unless you got 0, then you're in trouble, okay? Any questions? Okay? Yes? Okay? What I'm saying here is, f of n, let's look at the cases here. Okay? I don't think I've got it reversed. Let's clear the thing. Oops, let's try not to get that out. Let's clear it. Bunk. Okay? Here what we've got is that C, let's make sure, look at C times Gn is an upper bound to f of n. You see that? And let's go back now. C times, okay, I may reverse the names of these things. That's something I did reverse, right? But note that what matters is not the names of these things, but the relationship of the sign and the equal sign, right? This thing reads G of n is big O of f of n, meaning that a constant times this is an upper bound of that, right? And so, when you look at it, this was g of n equals f of n, big O of f of n. When I go back to this thing, clear ink, ka-chunk, here I had written down that f of n was big O of g of n. Okay? So there is no inconsistency in anything I have said. Any questions about that? Okay? Fair enough. Now, these definitions of upper bounds and lower bounds are a little bit slippery definitions. Okay? Because if you'll notice on all these graphs, there is kind of a weird thing happening, okay, with the lower parts of these functions, right? When I talk about if I am on upper bound of u, I am supposed to always be an upper bound of u, right? My age is an upper bound of the age of my younger brother, right? But on the other hand, with some of these functions, if you look at them, there's some funny behavior going low. We are interested in the behavior of functions as n gets very big, going out to infinity. Okay? And we are not interested in small potatoes values. Okay? So what we're going to assume when we make our big O, omega, and theta definitions, that implicitly it is okay if there is a constant n0, a small value n0, such that the relationship doesn't hold before n0. If we are saying that something is big O of something else if the upper bound relation holds for all values greater than n0. Okay? Any questions? Okay? So our notation here is about a notion of equality of upper and lower bounds where there are two parameters we are wiggling. One is the multiplicative constant that we use to jack up the thing that we want as our upper bound. The other is the input threshold, below which we don't care, and it can do whatever it wants. Okay? Any questions? Okay? Fair enough. Any questions? Okay, let's look at some examples here, and we'll try to catch this idea. Okay, so this gives us our real formal definitions, and so let's now read it and go to it all the time. We say that f of n is big O of g of n if there exists a threshold on the input and a multiplicative constant such that for all n greater than this threshold, right, f of n is always less than or equal to c times g of n. Does everybody see that? That's what that definition is. We say that there is an omega relationship if there exists this threshold and a multiplicative constant such that for all n greater than n naught, f of n is always above this thing. This is the lower bound relation. This is going to be a lower bound for this if, for a large enough value of n, f of n is always greater than or equal to c times g of n. And we say that there is a theta relationship if there are three of these things, a threshold, a first constant, and a second constant, such that for all large enough n, f of n is always less than c1 times g of n, and it is always greater than c2 times g of n. Any questions? These are definitions. If you go to the definition, you can solve anything because it's just a question of applying the definition. Any questions? Okay, let's look at some examples now. Okay? I claim that 3n, the function 3n squared minus 100n plus 6 is big O of f of n squared. This is a complicated looking thing, right? I don't want to talk about it. I don't want to even read it to you that much, right? But I am claiming that it is big O of n squared. Why is that? If that is true, there has to be some constant times n squared such that this side is always bigger than this side for all n greater than some n naught. That's what the definition said, right? What value of c will work in this inequality? Can anyone want to propose a value of c such that cn squared always beats the thing on the left? What would be a value? Someone said 4, right? 4 is a good value, right? Is 4n squared always bigger than 3n squared minus 100n plus 6? Well, no, why not? When n is less than 1, when n is equal to 0, right? This is going to be 6 on this side, and that's going to be on that side, right? But we don't care about very small values, right? But certainly by the time we get bigger than, let's just say 10, I mean, I can round it up, right? Once we get n bigger than 10, if this is equal to, oh, look at that, got erased, okay? 4, okay? This is going to be true. And therefore, okay, the relationship holds. Any questions about that? True or false? Is it the case that 3n squared like this is big O of n cubed? You say hope so? I don't know. Hope, no hope. I don't hope or I don't hope. I don't really have that much invested here, right? But I know that if I want to find out if it's true or not, what do I have to do? I go to my definition. This is going to be true if what? If there is some constant that when I multiply times n cubed, a c, okay, times n cubed, that it's bigger than 3n squared. Can anybody give me such a constant? Such that a constant times n cubed is always going to be bigger than 3n squared. Okay? Let's look at that again carefully. Is there a constant? I have here. Let's write it again. This is going to be true if I can find some c such that cn cubed is always going to be greater than or equal to 3n. Okay, you know, bigger than this. Okay, what's a value of c such that that's going to be true? Okay, yes. You say any c greater than 0. You want to say, let's say, what's a value of c greater than 0? We could pick 1. 1 is greater than 0, am I right? Is it clear that 1n cubed is always bigger than 3n squared? Let's think about it. Is this true? Let's take this, the important part of it. 3n squared. Is it true that 1 times n cubed is always bigger than 3n squared? No, right? For what's an example? I guess for n equals to 1, that wouldn't be true, right? But once you get past 1 to 2, 3, 4, when is it that this side is always going to be bigger than this side? When n is 3 or greater. Why is that? At n equals 3 or greater, at 3, this is going to be 3 times 3 squared, right? This is going to be 3 times 3 squared. It's going to be a tie at n equals 3, right? What's going to happen at 4? This is going to be 4 times 4 squared as opposed to 3 times 4 squared. Does everybody see that? And so at that point, this side is going to start dominating that side, right? So for all n, if I pick a constant of 1, 1 times n cubed is going to beat up on that side, right? And that's why we get the big O. Any questions about that? Okay. What about the other one? Suppose, let's try this thing, ka-chunk, clear. Suppose we look at the last one. is there any constant such that c times n is always greater than or equal to 3 times n squared? Is there any constant where that's always going to be true? Say no. Think big. What if c is 1,000,000? Okay? What if I put 1,000,000 here? Is 1,000,000n going to be bigger than or equal to 3n squared? For n equals 1, it's going to be bigger. For n equals 2, it's going to be bigger. Where is it that it's going to stop? This side is going to stop being bigger. Okay, yeah? Okay, at 1,000,000, what's going to happen at 1,000,000? This is going to be 3 times 1,000,000 times 1,000,000. This is going to be 1,000,000 times 1,000,000. So it's not quite 1,000,000 isn't quite big enough, right? But by the time we get up to 3,000,000, okay, 3,000,000 times this is, if we had 3,000,000 as my input, okay, well, oh, great. So what's going to happen at n equals 1,000,000? This is going to be 1,000,000 squared. This is going to be 3 times 1,000,000 squared. So 1,000,000 is not quite enough yet. Does everybody see that? But if you plug in 10,000,000 for n, okay, it isn't going to work either. Right, okay, I got myself correct. So there's no value of n here where this is going to win. And because of this, no matter what constant you pick, once n gets big enough, okay, this side is not always going to win anymore. Okay? So that says that there is no constant such that this will always win for bigger. And that's why we get the not equal to here. How many people are with me? How many people are not with me? Now, you may not be excited about this, but we're going through this in a slow, pedantic way. Any questions about it? Okay? This is how you reason for all of these problems. And again, once you get used to the notation, you don't have to work with it as much. Let's look at the omega example. What did the omega thing mean? This was lower bound, right? Lower bound meant that there existed some constant. Okay, let's look at the first one here. Some constant times n squared, such that cn squared is always less than, let's make it 3n squared. I don't know quite what happened here. Okay? What constant c can we use to multiply by n squared so that cn squared is always less than 3n squared? What constant would we use for c? What? What constant could we multiply n squared by so that it is always less than 3n squared? Yeah? 2 is a good number. Okay? Can anybody think of any other good numbers? 1 is a good number, right? 0 is not a good number because 0 is illegal. Does everybody agree with that? If I take any function and I multiply it by 0, then that wipes it out, right? So we're going to have to insist that c is greater than 0, okay? But any c greater than 0 will do the job, right? So since there is some constant 2, such that 2 times this is less than that, the omega relation holds. Is there some constant that c times n cubed is always less than 3n squared? Okay, let's think about it. Is there a constant I can multiply n cubed by to make that less than 3n squared? Okay. Is there? If I make it 0, yes, that would be true. But even if I make it 0.00001, okay, at some point, okay, for a big enough n, by the time n is the reciprocal of this thing, I will still have 2n squared, and that will clear out this other thing. right? So there is no constant here, okay, such that I can multiply it so that this times n cubed is always less than that. So we get that this is not in omega of n cubed. Any questions about that? Okay. What about the last case? Is there some constant for this omega to be true? That means that there is some constant times n, such that this is always less than 3n squared. Okay? Is that possible? Is there a value of c such that cn is always going to be less than 3n squared? Yeah? All values? Okay. If we make it 1,000,000, that would certainly work, right? Okay. If we used 1,000,000 times n, certainly there is a value of n such that this is going to take off and beat it. Of course, in thinking about it, I'd probably want something simple, right? Like if I had 3n squared, it's probably best to compare it to 3n, right? Then it's obvious to me that for all n, this is going to be true, right? What about n between 0 and 1? Well, that's why I don't like to think about it. That's why I say it's n greater than n naught, right? For a big enough n. Because again, there's weird things. This is why we're doing it. Because there's weird things that are happening at small n that we don't care about, right? But for a large enough n, there exists a constant such that this times this is going to be a lower bound to that. We say it's omega. Any questions? And finally, clearing. When we talk about theta, okay, what we're saying here is that 3n plus this squared plus this funny thing is theta of n squared, because as we worked out before, there is a constant such that c times n squared is bigger than this, namely 4, 5, 6, and there is a constant that we can multiply by this where this is less than this. Okay, 2, 1, 2, 1.5, right? So because it's both big O and big omega, we say that it is theta. Okay? And that means that when we say that this function that we care about is theta of n squared, what we're really saying is that we have a tight bound on it, this complicated thing we don't want to reason about. When we say it's theta of n squared, we means it grows basically quadratically. Okay? Any questions about that? Okay? For the other functions, we don't see that. If we compare it to n squared cubed, this is not theta of n cubed, okay? Because although c times n cubed is bigger than it, giving the O, we don't have the lower bound omega relationship. Likewise, comparing n to this, okay, we have the omega relationship because this is a lower bound of that, but this is not an upper bound of it, okay? So thus, of all these functions, the only one we can talk about as being quadratic, okay, is this one. Any questions about that? How many people think they sort of get it? Okay, again, this is pedantic and dumb, and the way you've got to work through when you're given a problem is you go back to the definition for now, okay? But we're going to use the big O notation to talk about, as a simple way to talk about complicated functions. And the complicated function we care about most in here is the worst case running time of the algorithm. We could talk about other things. You could talk about the wealth of Bill Gates as a function of time, right? That's a function. And you can look at what the upper and lower bound is. Or as a better example would be your credit card debt. Okay, you take your credit card. You put $100 in there. You walk away for a year. What's going to happen? Your debt is going to change as a function of time. Okay? If we talk about what is the upper bound, what is the lower bound on that? We can say it's big O of some constant to the n. It's an exponential function. That's why credit card bills grow very quickly. Okay? Any questions about that? Yes? Okay, so what you're saying here is, suppose I talk about an algorithm. For example, let's talk about it. You guys have been in here. You're saying, okay, what you're saying is that upper bounds don't have to be tight, is what you're saying. Okay? So let's think about what he's saying. In here, in the algorithms world, some of you have said that you have learned something about sorting. Is there any algorithm that you have known that is sorting is n squared time? What sorting algorithm takes n squared time? Does anybody know? Yes? Bubble sort, okay? So what do we know? Let's let f sub n equal to the running time of bubble sort. Right? In fact, we know that there is some constant times n squared such that this is greater than f of n. That is why f of n is equal to big O of n squared. Does everybody see that? Now, it is also true that there exists some constant times n cubed such that c times n cubed is bigger than this, right? So we could also say that f of n is big O of n cubed. Does everybody see that? When we talk about the big O notation, we are talking about an upper bound, right? That's all that it is, right? If I have something as an upper bound and I take it bigger, is that also an upper bound? So it is perfectly fair for me to say that bubble sort takes order n cubed time, right? Does everybody agree with that? It's big O of n cubed, right? The worst case running time. It's perfectly fair to say it's big O of n cubed to the fourth. That's certainly a true statement. Does everybody get that idea? If you don't, let's talk about that. Here is the running time of bubble sort, right? It's going to go something like this. Here is a constant times n squared. Here is a constant times n cubed. Here is a constant times n to the fourth. All of these are upper bounds, right? So if I say that the complexity of the worst case running time of bubble sort is big O of n to the fourth, does everybody see I am making a true statement? Does everybody see I am also making a boring statement? Yes. Okay? That a better statement is the tightest bound that we have, right?
That's why
we invented theta to say when we know we have a tight bound. In fact, for bubble sort, a constant times n squared is an upper bound on the running time of bubble sort. It is also true that there are inputs to bubble sort that will take some constant times n squared time. So in fact, the worst case bubble sort complexity is n theta of n squared. We usually say big O out of sloppiness, okay? But we want the lowest upper bound possible when we analyze an algorithm, right? And that is the one that is most interesting. Any questions? Okay, any questions about this notation or what I was just saying here? Okay, fair enough. Oops, bunk, clear. So let's look at a couple of other things. Actually, just to make sure we don't confuse people too quickly. Note that when you multiply, if you have a function, and you multiply it by a constant, okay? If C isn't a constant, 2, 3, 5, 17, a million, if I multiply that constant by, if I have a function f of n, and I multiply it by a constant, 1,000,000 times f of n, note that that doesn't change the theta relationship, right? 1,000,000 times f of n is theta of f of n, right? So multiplying a constant times something doesn't change the big O-ness, right? If you think about it, if you have a computer that runs twice as fast as your old computer, has the complexity of your algorithm, the worst case number of steps, really changed? It's gotten halved, but that's sort of within the slop of the big O notation, right? So we're not interested in its change of whether something has gone up by a factor of 2 or down by a factor of 2, right? So what's great about the big O notation is that it ignores, we can ignore multiplicative constants in front of things. They just clutter it up, right? However, Monk, that's right, okay, good. When we take two functions that are not constants, that do depend upon n, and multiply them together, okay? In fact, that's when it changes the big O notation, right? 3 times f of n is going to be big O of f of n. But f of n times g of n is going to now be, okay, order f of g of n. Why is that? Go back to the definition. Saying something that is order f of n means that there is some constant c1 times f of n, such that this is an upper bound, right? This thing being ordered g of n means that there is some constant c2 times g of n, okay? Such that this is an upper bound. What is going to be an upper bound of f of n g of n? C3, or specifically C1 times C2 times f of n times g of n. Does everybody see that? That if this thing is always, if 2 times f of n is always bigger than this, and 3 times f of n, g of n is always bigger than this, then 6 times this, f of n times g of n, is always bigger than that. Okay? Any questions about that? Okay? So learn to reason. Again, the way to interpret this is, if I think about it as running times, this would be saying, what if I am doing f of n things, each of which took g of n time, right? How much time will it take? If I am doing at most f of n things, each of which is going to take at most g of n time, the total amount of time I take is going to be at most f of n times g of n. Does that make sense? That's exactly what this is reasoning about, right? Look at the second one. If I am doing at least f of n things, each of which takes at least g of n time, the total time that it's going to take me. If you're doing at least 10 homework assignments in the class, and each homework takes at least 10 hours, you are going to be working at least 100 hours in here, right? So that's not quite the math necessarily for the class, but does everybody see what the reasoning is? See how this property of reasoning about upper and lower bounds is the kind of reasoning we want to do when we think about the complexity of algorithms. Any questions? Okay. So this is not the most exciting lecture we're going to have in here, but it's important you guys get comfortable in working with the notation. So work on it, read it, and I'll talk to you about it at with the problem of the day next week. Thanks for your attention. Yeah, okay, hold on.